Controlled environment, plant production, engineering, technology, education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA, NEFA, through their Higher Education Challenge Grant Program. This presentation is about basics of greenhouse environmental physics, and this is part 1. This module is presented by Dr. Murat Kasira of the University of Arizona, Dr. A.J. Boat of Rutgers, and Dr. Cherry Kubota of the University of Arizona. By the end of this module, you will be familiar with the basic principles of greenhouse physics, conservation of energy and mass in greenhouse system. We'll talk about mass and energy transport mechanisms, and you will learn about energy balance in greenhouse system. Growth conditions inside the greenhouse are dependent on local solar radiation, carbon dioxide concentration, temperature, and water vapor in the air. Since the greenhouse is enclosed, all these factors are controlled by the glazing because it envelopes the air and reduces the air exchange between the greenhouse and the surrounding environment. The glazing also controls the transmittance of radiation, both from and to the greenhouse. The greenhouse can either be an open system with a design that aims to exchange mass and energy with the surroundings, or it can be a closed system which restricts mass and energy transport to the surrounding environment. In order to understand the full effect of covering on the growth conditions inside the greenhouse, the mechanisms of mass and energy transfer must be understood and applied appropriately to the greenhouse applications, which allows us to study controlled environments. To consider energy and mass transfer, the conservation of energy and mass must be discussed. First, we will consider the concept of conservation of energy and then draw an analogy to mass conservation. Let's consider this box as our system and look at the energy exchange processes. For any balance, the general equation can be simplified as follows. We can consider energy input to the system, energy output from the system, and we can consider energy generation and consumption in the system. Then the energy balance equation is summarized as input minus output plus generation minus consumption, and that equals to accumulation. In the case of steady state, where variables are no longer time dependent, the accumulation will equal to 0. In general, considering a control volume, in this case greenhouse is our control volume system, if an energy flux enters the control volume, or if heat is generated within the system, the overall internal energy of the control volume will increase. In the same logic, if energy flux leaves the system, which is a negative flux, or if energy is consumed within the system, the overall internal energy of the system will decrease. Examining these fluxes and comparing them and considering other sources of energy increase or decrease is called performing an energy balance. Doing so for mass concentration fluxes is called performing a mass balance. In the case of an energy balance, the equation becomes the heat input minus the heat output from the system plus heat generation minus heat consumption, and that equals to the rate of heat transfer. Where the heat input, for instance, can come from air entering to the system, the heat exiting the greenhouse can be a result of air leaving the greenhouse. For instance, the heat generation can be a result of a heater, and heat consumption can be a result of aerobic cooling. The internal energy in the system, the Q, can be directly related to the temperature through considering the heat capacity of the volume, the Cp. And using the following equation, Q equals to Cp times T, where Cp is the specific heat of the system and T is the temperature of the system, we can determine the internal energy. So it is clear here that the temperature can be used as an indicator of the energy of the volume of interest or greenhouse system. In a mass balance, the equation is similar to the energy balance. The equation becomes mass into the system minus mass out of the system plus mass generated within the system minus mass consumed within the system, and that equals to the mass transfer. In the case of greenhouses, the mass balance of interest is the water vapor balance. Similar to heat, water vapor enters and exits the greenhouse with the entering and exiting air. Water vapor can be generated through evapotranspiration, for instance from a crop canopy, or it can be consumed through condensation. The mass flux of a substance to and from a control volume can be related to concentration of that substance in the volume as follows. M equals to V times Ca. Here M is the mass, V is the volume of the system, and Ca is the concentration of that substance in the control volume. So from this relationship, it is clear that concentration can be used as an indicator of mass in the volume of the greenhouse. To relate the in, out, generation and consumption terms in the balance equation to their respective indicators, it is important to understand the different mechanisms of energy and mass transport to and from a volume. Generally, energy is transported from high temperatures to low temperatures for all mechanisms. Here are the main forms of energy transfer. Energy transfer through conduction, which is the transport through a resting medium, solid, or through a fluid not in the direction of the flow. Convection, which is the transport through a fluid in the direction of the flow, or transport from a resting medium to a moving medium. Radiation, for energy only, which is the transport between surfaces of opaque bodies by electromagnetic waves through transparent medium. Let's discuss about mass and energy transport mechanisms. First, we're going to talk about conduction. Conduction is the mechanism of transport in a resting medium. The mechanism itself is on a molecular scale, but for oral calculations and our discussions here, the process is considered at a microscopic scale, so we can quantify it. In greenhouse, conduction takes place through the construction and cover, but it is especially important in regard to the transport in the soil as well. In general, energy flows from high to low temperature for all mechanisms. For conduction, we not only pay attention to the change in temperature, but we also look at the distance over which the temperature changes. The temperature change over a given distance is called the temperature gradient. The Fourier law states that the transport of energy in one direction, for instance, as you can see here in the x direction, is proportional to the gradient of the temperature. The proportionality factor in this equation is called the thermal conductivity. The negative sign that you see here in the equation indicates that the heat transfer is in the direction of decreasing temperature. Again, in this equation, the Q conduction is the heat flux by conduction, and lambda is the proportionality constant, which is the thermal conductivity of the material. The transport of energy and mass by a flow from one place to another in the direction of the flow is called advection. The advection and the transport from a surface to a flowing medium are called convection. In a greenhouse, the ventilative exchange of energy and mass, for instance water and carbon dioxide, is transported by advection. The exchange between the greenhouse air and the internal surfaces, such as crop, the greenhouse cover, heating pipes, and soil surface, is a transport by convection. The same holds for the exchange between the outer surface of the greenhouse and the ambient air. So the net energy flux from inside to outside due to ventilation process through a ventilation opening can easily be calculated using this equation. And here the net energy flux from inside to outside due to ventilation is called Q advection in our example. So the Q advection equals to F volume times Cp times delta T, the temperature difference between inside and outside of the greenhouse. And in this equation, the Q advection is the heat transfer due to ventilation. F volume is the air volumetric flow rate. Cp is the volumetric air specific heat, and temperature difference is also represented by this term. So for the mass flux by ventilation process, the same kind of relation can be set up. Here, for the mass flux due to ventilation, we can use this equation. M advection equals to F volume times the concentration difference. In this equation, M advection is the mass by advection, F volume is the air volumetric flow rate, and C in minus C out is the concentration difference between inside and outside of the greenhouse. Here you can consider C in and C out as the inside and outside concentrations of the water vapor or carbon dioxide. The transfer of energy or mass from a surface to a flow field cannot be described in a very easy way. Because of that, a more practical description needs to be developed, knowing that the driving force for the transport due to convection is the temperature or concentration difference between the surface and the flowing medium, it is simply stated that for energy transfer, the heat flux density can be represented with this equation. And we're going to call the heat flux density as Q convection in our example. So the Q convection equals to alpha times the temperature difference between the surface and the fluid. In this equation, the alpha represents the convective heat transfer coefficient. For mass transfer, the mass flux density, which is represented by m convection in our example here, equals to K times the concentration gradient between the surface and the fluid. And here in this equation, the K indicates the convective mass transfer coefficient. In greenhouse applications, symbol E is used instead of m convection to describe evapotranspiration. The energy and mass transfer coefficient depends on a number of factors. The challenge is to find the correct coefficient to use in your calculations based on experimentally verified data. These factors include the properties of the flowing medium, the flow conditions, and the geometry of the flow field. In order to find the convective heat transfer coefficient, alpha, the Nusselt number is used. You can solve this equation to determine the convective heat transfer coefficient alpha. In the Nusselt number, lambda indicates the thermal conductivity, L represents the characteristic length or the characteristic dimension of the surface. Selection of the characteristic length should be in the direction of growth or thickness of the boundary layer. For instance, some examples of characteristic lengths are the outer diameter of a cylinder in external cross flow perpendicular to the cylinder axis, the length of a vertical plate undergoing natural convection, or the diameter of a sphere. When the fluid flow is caused by external factors such as pressure gradients causing wind over a greenhouse, the convection is called forced convection. The flow conditions and geometry of the flow field is characterized by the Reynolds number. The properties of the flowing medium are characterized by the Prandtl number. We can use Reynolds number to indicate if the flow is laminar, transient, or turbulent. As you can see, the ranges of Reynolds numbers, for instance, Reynolds numbers less than 2000 defines a laminar flow, or a Reynolds number between 2000 and 4000 determines a transient flow. In the case of turbulent flow, Reynolds numbers are higher than 4000. The Reynolds number and the Prandtl number are related to Nusselt number with the following equation. In this equation, the C, N, and M are constant coefficients that are experimentally determined depending on the conditions of the flow. For air, Prandtl number of 0.72 is generally used. For low ranges of Reynolds numbers, for instance 10 to 2 or 10 to 5, we can use this equation, while the Nusselt number equation takes this form for a Reynolds number ranging from 10 to 5 to 10 to 7. Since these equations are a result of laboratory experimentation, it is necessary to modify them to apply to greenhouse settings. Similar to the Nusselt number, the Sherwood number is defined with this equation, where L is the characteristic length, as we discussed before, and D is the diffusivity of the component in the medium. If the Sherwood number is known, then we can determine the convective mass transfer coefficient, which was defined as K before, by using this equation. Using a similar approach, the Sherwood number is also determined using an analogs equation, using, for instance, this equation, where the SH is the Sherwood number and SC is the Schmidt number. The Schmidt number also characterizes the flowing medium properties. In regards to the value of C, N, and M in the Sherwood equation here, they are all same as those explained in the Nusselt number equation in the previous slides. For different ranges of Reynolds numbers, we can use different forms of Sherwood equations, as you can see here on the slide. In many cases, the flow may not be caused by external factors. Instead, temperature and concentration differences may cause the fluid to flow in a convection, and this is called natural convection. In the case of energy, determining the convective transfer coefficient is still possible through the Nusselt relationship, except there is a necessity to include a number that would characterize the temperature difference in the flowing medium. This number is the Grashof number that is defined with this equation, where G is the gravitational acceleration, delta T is the surface medium temperature difference, L is the characteristic length, T is the medium temperature, and V is the kinematic viscosity of the fluid. Similar to the case of forced convection, these relationships are simplified with a more comprehensive analysis of multiple surfaces and flowing fields in a greenhouse. Phase change involve both mass and energy transfer simultaneously. This is of interest especially for consideration of the process of evaporation and condensation. If water evaporates, the water vapor will be transported from the evaporating surface to the undisturbed air according to the transfer equation which we introduced in the previous slides for the vapor flux density. And we need energy for evaporation. The heat of evaporation can be introduced into this equation, as you can see with this H-evap term. Based on the equation for vapor flux density, assuming that this vapor flux density is the result of evaporation, then the total heat required for said evaporation can be determined by the equation presented here. This energy is extracted from the surrounding air by convection, and this localized energy balance then becomes an equality, as you can see with this equation. Using the previous Nusselt and Sherwood relations, it is possible to determine the convective heat transfer coefficient, the alpha, as well as the mass transfer coefficient K. Radiant energy is emitted by a surface through an electromagnetic waves depending on the nature of the surface and its temperature. The Stefan-Boltzmann law states that the total energy emitted over all wavelengths is proportional to the fourth power of the absolute temperature of the surface. As you can see in this equation, the epsilon is the emissivity and the sigma is the Stefan-Boltzmann constant. Ts defines the surface temperature. The emissivity describes the emitting properties of the surface. For instance, a black body has an emissivity of 1. Let's look at radiation between two surfaces. In the case of multiple emitting surfaces, the surfaces emit radiation with wavelengths in the thermal range, which get absorbed by other surfaces and in return emit radiation. In the case of two surfaces, the net radiant energy can be calculated using the following equation. The effective emissivity, represented by epsilon 1 to 2 between the surfaces, depend on the individual emissivities epsilon 1 and epsilon 2 and the geometry of the surfaces. For large parallel surfaces, a relatively simple relation can be used to evaluate the effective emissivity, as you can see in this equation. The greenhouse scenario, however, involves many surfaces and many different material types, so additional relations need to be used to simplify the situation to quantify the scenario accurately. Now let's look at the relationship between energy and wavelengths. The radiant energy consists of different wavelengths which depend on the temperature. At low temperatures, the electromagnetic waves tend to be concentrated in the infrared region at lower energy with longer wavelengths, while higher temperatures emit waves concentrated in the visible and ultraviolet regions at higher energy and shorter wavelengths. If radiation falls on a body, generally part of the radiation is absorbed in the body and some part is reflected, some part is transmitted, and some part is emitted to the environment. A radiation energy balance can then be studied at steady state condition, as you can see in this equation. So the total radiation equals to the sum of the transmitted, absorbed, and reflected portions. Assuming that the absorbed radiation is equal to the emitted radiation, then the energy balance can be rewritten with this equation, as you can see here. If we define the reflectivity with rho and emissivity with epsilon and the transmissivity with tau, and assuming that the incident radiation is 100%, then the energy balance is then simplified using this following equation. Within a greenhouse environment, the opaque structural parts of the greenhouse mostly emit in the thermal waveband, even if they absorb other wavebands provided by solar radiation, for example. You can find further details of our discussions in this module using these references: greenhouse climate control and integrated approach, greenhouse technology and management, and greenhouses, advanced technology for protected horticulture. We would like to acknowledge the funding received for our effort by the USDA NIFA program.